All right, everybody. Thank you very much for coming out tonight. Again, our deepest apologies for taking a moment to get set up. Today we're going to be talking about maximum likelihood estimation, backpropagation, and a quick little introduction to CNNs. Now, you might not recognize those terms. That's okay. By the end of the night, hopefully you will recognize all those terms. Before we get started, a couple of real quick announcements. The first is that we have an event tomorrow. This is going to be an event with Dr. Alyssa Adams. It's going to be focusing on the intersection of AI and biology. It's going to be tomorrow, 6 to 7. You can RSVP at that link there. And also the Zoom link that you can join into that event is right there as well. All of these details are also on our Discord server. Also, in case you missed it, workshops is different this quarter. We have a new format. We're doing both theory and applied track. So you guys are here. This is theory track, where we're going to be focusing on, as the name suggests, more of the theory, and really we won't really be doing much, if any, coding in these workshops. This is going to be most like the math and what actually is going on behind the scenes. But if you're also interested in experience with actually building these ML models and training them, that is what applied track is for. It is, instead of Mondays, Wednesdays, 6 to 8 p.m., and then it's at Lacrette's 110. So not the same room, unfortunately, but feel free to come by. If you've missed the first couple applied tracks, that's a-okay. We're here to cater to you guys, and unlike with past iterations, it's absolutely we've tried to design this in such a way that you can miss workshops, and it'll turn out just fine. And then if you are also interested in doing our projects track with our larger and cooler projects, for next quarter, we are planning on making applied track mandatory and theory track heavily recommended. But technically you can get by without it. And then just to reiterate, applied track is just if you want the practical bare bones knowledge of AI, and you'll be working through 4 self-paced notebooks, specifically an Intro to Python notebook, a Neural Networks notebook, a CNNs notebook, and an RNNs for text classification notebook. Now, if you already, know everything about Python, perfect. You can just skip straight to neural networks with MNIST. If you already have made, 1 or 2 neural networks, but you're looking to do something a little more complicated, that's what our CNN notebook is for. And then, finally, if you feel like you're pretty good with, image classification, but you want to learn a little bit about text classification, that's what the RNNs notebook is for. And, you don't have to go through all of them. We trust you to go to the level that is appropriate. And then theory track, this is what you guys are here for. We'll just, that's how the neural networks are actually working, what all this, code that you're writing is actually doing behind the scenes. And this will hopefully build you a really good foundational understanding. Now, this week, we're going to be going over, as I said, maximum likelihood estimation, backpropagation, and an introduction to CNNs. That's where we're at. This is our tentative roadmap for the rest of the quarter. Subject to change. And also, if you have any topics that you are really interested in, feel free to let us know. This is our first quarter doing this, and so if you think that there's something that we should be talking about that we don't have up here, or you think that we should be doing it in a different order, we'd love to hear the feedback. So I'm going to hand it off to Liu now, and he's going to start getting into the actual theory of it all.
We'll just use the slides. So today we're going to be talking about maximum likelihood estimation. This is sort of another way of looking at, another lens to looking at linear regression, softmax regression, and logistic regression from a probabilistic approach. So rather than looking at it from minimizing a cost function, we're going to look at it as maximizing a certain probability. And also, I want to give a shout out to Andrew MG. He's the G. His course on machine learning, it's a grad course, it's called 229. The notes online are really, really good. And I would definitely suggest, if anyone wants to have a look at it, he explains a lot of the math really well. Even though the math isn't too in-depth in terms of proofs, he does give a good general overview of the topics, I would say. So if you guys want to check that out, go ahead. So before we start, I would like to start with some questions that we're going to answer today, at least in the MLE topic. One is, why is a least squares cost function a reasonable choice, right? Why do we have this sort of square thing where we take our output, our parameters multiplied by our input, and then we subtract it from our optimal output, and then we just square it, right? Why is that a reasonable cost function? You know, why is this reasonable? Why wouldn't you use any other cost function, right? Sorry, loss function. And we'll explain why this is and why this is a very natural way of approaching this. We'll also explain why do we use sigmoid and where does it come from? You guys might be also wondering, you remember the equation that we had before with the weird exponential, why are we using it? Where does it come from mathematically and so on? We'll try to give you guys an intuitive sense. And also, why is softmax a natural method for multi-classification problems and where does that come from? So we'll explain that. And sort of getting into it, do you guys remember this previous example that we were talking about last class? Can anyone explain this a little bit? You guys remember this? The linear regression example? Does anyone know what this is? Data? It's like this matrix. So these are just your parameters, right? And this is one of your training instances. So this is one training instance for let's say you have 100 training instances. This might be the first one, for example, right? And you're just having a matrix multiplication between your parameters and your input, and then I'll explain what this is later. But normally you just have this and you'll be equal to the output, right? And if anyone knows what a linear combination is, it's effectively a linear combination of your parameters where your coefficients are just your inputs. And we're gonna look at this from a different approach, because usually when we talk about linear regression, we have this. But now we're gonna think about it from a different approach, right? We're gonna add this epsilon I term. And this epsilon I term effectively represents unmodeled data or random noise, right? So, if you guys are wondering, what is random noise? What is unmodeled data? Right? One good example is, for example, suppose you have a physics experiment, right? And then in your physics experiment, you have a sensor, right? Your sensor has random data. And so, as you're collecting data, there might be all these anomalies that occur in your data set, right? Have you guys ever used Excel? I'm guessing you guys have. You guys have had a best fit line, right? Right? The best fit line and the polynomial line, they use linear and polynomial regression, right? And it's all based on this equation. They use something called a closed form solution, but it's still based on this equation, right? And what we're seeing here is all the noise that you can have while filling that in. So this is what we're going to answer. And so, deriving least squares from maximal likelihood, I'm going to sort of breeze through this. If you guys have any questions, let me know. And at the end too, we can talk about this, because this gets, a little bit math heavy. Oh shit, sorry. Yeah, I forgot to go through the Gaussian distribution. So this is the Gaussian distribution. This is a famous distribution we have here. This is just the mean and probably density. And then this is just a standard deviation. And this is the function equation. We're going to see this again and again and again. One of the really helpful things about Gaussian distributions are when you're writing math proofs, they're really easy to work with. One thing, and also while linearly combining them, it's linearly combining them, the expected values is much easier, so it gives you a smoother experience. We'll get into that. So let's talk about deriving the least squares from maximal likelihood. So right here we have the likelihood equation, likelihood of theta. And I want you guys to sort of shift your viewpoints now to rather than minimizing a cost, maximizing a y given an x. So you want to maximize the probability of getting something given another thing, right? So have you guys ever heard about like conditional probabilities? So that's effectively what this line is, right? This line is, your y, meaning your output, and your x, which are all your training instances, right? And you're maximizing the probability of getting a certain y given an x with a parameter theta, right? So what you're changing in this case is theta. So you're trying to estimate a better theta so that you have a higher probability of getting the y. You see what I mean? So we've sort of inverted it right now. We're working with maximization problem rather than a minimization problem, which is really interesting. And we go from this, assuming that the probabilities are independent. I think that's the reason, yeah. Assuming that the probabilities are independent, we can take the product of the probabilities, and that's what's happening here. We take the product of every single training instance, and that's our likelihood function. And all we want to do is we want to maximize this likelihood function with within terms of theta, which is your parameters. And you guys remember when I said before that this epsilon can be thought of in a normal distribution, right? If we think about it as a normal distribution, we can also implicitly imply that our output follows a normal distribution as well. So then we can represent this probability in terms of a normal distribution and then take the product, right? And this, it's kind of weird. When I first read this, I was like, I didn't really understand it, but it turns out you can really do this, right? You can express it as a normal distribution where the mean is just, your output, so your parameters times your training instance. And the way I like to think about it intuitively is sort of like when you're doing linear regression, you're fitting a line into data, right? That's all that you're doing. You're just fitting a line into data. And that line is in many ways it's not expected but it's kind of like that. It's the best, it's sort of like the mean of your data set, but not really. And that's how I think about it intuitively. It's that's why you look at this as the mean of your model, and then you just take the product of that. Does anyone have any questions on this specifics? Does have any questions? Okay. So now let's derive least squares from our likelihood. So if you remember the previous equation, this is a product, and products are kind of messy to work with. So we want to convert it into a easier thing to work with, and that's a sum. So if you take the log of a product, you can convert it into the sum, right? So right here, you take the log of the whole product, and then it's converted to a sum, right? This is the sum of the logs, right? And to go from here to here, it might look a little bit messy, but it's like relatively simple. All that you're doing is just you're separating this term because it's a log of the whole thing, and you're just separating it into log of 1 over 2, the square root of 2 pi, your standard deviation, and the exponential. And then you're simplifying the terms. And does anyone see a term that we're familiar with that we were talking about before? What?
It's mean squared error.
Let's go. Mean squared error. That's what it is. Yeah, it's mean squared error. So you have your mean squared error right here, right? And there you go. We derived least squared from this sort of maximum probability perspective, right? You guys might be wondering this. If you set it to the right constants, this will cancel out, and you're only left with least squares, which is kind of beautiful, right? Like this thing came from a much more natural perception of linear regression. So if you were wondering where least squares come and why do we use least squares, this is the reason. This is one of the fundamental reasons, is that a least squared problem is effectively and essentially a maximizing probability problem, where all you're doing is you're just maximizing the probability of getting a y given an x with certain parameters theta. That's all that you're doing. So effectively, that's like what it boils down to, right? So yeah.
Explain again what's the issue for using Gaussian PDF as a like.
Wait, can you repeat that?
Like, can you repeat again the intention behind using the Gaussian PDF as a like function?
So yeah, let me go to the previous. So you're saying, why do we interpret that our model has a Gaussian distribution?
Yes, and why use P equals this stuff?
Why use P equals this? So that's the assumption, right? We implicitly assume that our model has a normal distribution. If we don't assume it, this proof won't work. It won't reduce to this case. Because we assumed that our model has a Gaussian distribution, we can change this probability, the probability of getting a y given an x, into the Gaussian distribution where the mean is our theta p times x, because that's our output. Does that make sense?
And the nice thing is, you'd be like, well, what if it's not a Gaussian distribution? The thing is, you are the one who's initializing the model, right? You're the one who's determining what the starting parameters are. That is why when we usually initialize models, we try to initialize with some sort of Gaussian distribution, is because, first of all, nice math, but secondly, theoretically, at least in smaller scales, we've shown that Gaussian distributions work really well.
And to further add to that point, it doesn't mean that your data set has to have a Gaussian distribution for linear regression to work. It doesn't have to. It's still, linear regression still works for data sets that don't follow this, this pattern. As Jordan was saying, it makes it much easier to derive and to formulate. Yeah. And yeah, we already explained this. Now deriving logistic regression. So just a side note, logistic regression is technically not even really regression. It's because normally when you're working with linear regression, you have a bunch of data and you're sort of focused on predicting future data in sort of this like continuous interval, right? While for logistic regression, it's another perspective when you're trying to classify points. So you're trying to classify, for example, this is kind of crazy, but a cat and a dog. You wouldn't do logistic regression for a cat and a dog, but let's say you are trying to classify a cat and dog. That's a classification problem, right? When linear regression is used more, for example, housing prices, right? That's a linear regression problem. And so deriving a logistic regression using maximum likelihood estimation for the parameter data, this is how you would do it. And yeah, you start off with the probability distribution of your model, which in this case, probability distribution is the Bernoulli distribution. Do you guys know what the Bernoulli distribution is? That's great. So this is the Bernoulli distribution. You have your hypothesis function, which raises it to your output, minus your hypothesis function, minus y. And then you set up your likelihood function, maximum likelihood function, and then assuming that it's independent, you can turn it into a product. And let's go to the next page. We're sort of going to breeze through this a little bit. This is all the ugly math that gets involved into calculating it. But effectively, once you go through every single step, you're going to lead into, again, a least square solution for your logistic equation. But the beautiful thing is, even after you go through all this, least squares again comes back. And the update rule is almost exactly the same. The only difference is that your hypothesis function now, it's not just theta x, there's also the logistic, there's also the sigmoid function around that, but it doesn't affect it too much because the logistic equation has, the sigmoid function has a very easy derivative. But yeah, this is the math related. And if anyone wants to know like the specifics, I can show them this. This is actually really interesting. And we'll explain some specifics on this as we go along. Another question you guys might have is, why do we use the sigmoid function, right? Why do we use this like 1 over 1 plus e raised to the power of negative z for logistic regression? And the reason is it's actually a very natural, wait, do you have a question? It's actually a very natural way of looking at classification problems because it comes as a as an effect of looking at your models through a certain family. We'll explain what that family is. It's called the generalized linear model family. We'll explain why that is. And effectively, if you think your model has a binomial distribution, right? If you think it has that distribution, sigmoid just comes naturally out of that. So, machine learning scientists, they didn't just BS it. There's a reason why it comes about. So this right here, give me a sec. So, okay, this right here, these are called generalized linear models, and they have two parts, right? One is the probability distribution, right? For example, before I was explaining about linear regression, you can think about it as having a normal distribution, right? Logistic regression, you can think about it as having a binomial distribution, right? And any distribution, any model that has a distribution that we put into this term, this kind of like a little bit ugly equation, is part of the generalized linear models, right? So they're all part of this larger set of models. And yeah, these are the different parameter names. It's really simple. It's when you look at it, it's actually really simple. They all boil down. And another thing that I want to know is this equation right here. This equation is very important. Do you guys know what an expected values? You guys know what expected values? Okay, that's good. So this is all that this is saying is that the expected value of getting y given x is equal to, mu or the mean, which is just equal to the inverse of, now looking at it's kind of long, x times beta, and beta is just your parameter, right? And this is what, the generalized linear model, this is what connects all of them. This part specifically is called the link function. In the case of logistic regression, for example, the link function is called sigmoid. In the case of softmax, the link function is the multimodal probability function, and so on. So they're all part of the same generalized linear models. And a look into the sigmoid function, right? So the sigmoid function is a consequence of the relationship between the mean of a Bernoulli distribution and the natural parameter n. In this case, n is just this theta. This is bad notation. This is the theta transpose times x, right? And then if you take our model, the kind of expected value of it is going to be equal to this, because that's what we're trying to estimate. That's what we're trying to get to, which is just our model, right? So we have 1 over 1 plus erase our negative and the natural parameters, which is just this. And so that's where this comes from. It's just a consequence of the fact that the Bernoulli distribution, the relationship between phi and theta x is the sigma. That's all it is. If you guys want the derivation of this too, we can show you guys how we derived this, but that's where this comes from. It's just a natural consequence of it. Yeah. So what about softmax, right? So before I was talking about how logistic regression is used for binary data, for binomial distributions, softmax is used for a multinomial approach. Rather than looking at it from a binomial approach, you're looking at it from a multinomial probability distribution, right? And so in this case, your probability density function is going to be for multiple dimensions, and you're gonna look at multi-dimensional probabilities. And then again, this is just a natural consequence of this generalized linear models. That's how you bring softmax. So everything, it's actually crazy. Everything comes from these set of exponential distributions. And so we kind of want to give you guys a sense of what softmax is. Like a lot of models use softmax at the end. Neural networks do it. There's also something called softmax regression. We have multiple classes. All that softmax does is it takes your output and then it puts them in terms of probability. And the way it puts them in terms of probability is it sums up their exponentials, and then for every exponential divides it by that. So this right here, so the normalizing factors, so they all add up to 1. You guys see why that is, right? And yeah, that's the softmax. And you guys might be thinking this might add nonlinearity to your neural network, but that's not really the case, and we'll explain why that is. And this is cross-entropy loss. This is a function for cross-entropy loss. This is also used in many multi-classification models. This is your true probability, your one-shot probability, and your model's predictive probability distribution. And then we just sum it over all the classes. The reason why we're taking the negative is because we're trying to minimize this, right? We're trying to minimize the loss, and so we want to take the negative of a logarithm, and in this case, all p is less than 0, so this is going to be negative. So we want to make it positive so you can minimize it. And that right there is cross-entropy loss. I'm breezing through this a little bit too fast, but a lot of models with multi-classification, let's say, for example, you have an image of a cat, a dog, a squirrel, I don't know, just random animals, you'd probably use cross-entropy at the end of your neural network because it's very helpful and very powerful for multi-classification problems. And, specifically for cross-entropy, one of the reasons why machine learning scientists really like cross-entropy is because the derivative is really simple. Because effectively what cross-entropy is it's a softmax function followed by something called a negative log likelihood function. So you're just bringing those two functions one after the other, and the derivative is really simple. So the derivative calculation, the gradient calculation is actually really simple at the end. And it's you literally just take your true value, your optimal value, subtracted by your y, and that right here is your derivative between the logics and the output of your cross entropy loss. And usually for PyTorch, your cross entropy also includes your softmax. So it's not just just cross entropy, it's also cross entropy included with softmax. Does anyone have any questions on this?
And just like real quick. So like, what do we mean by say PyTorch does the softmax for you? So if you remember, like one of the things that we're stipulating is, hey, we want the output to be a probability distribution, and the way to do so is using the softmax function, right? And the reason why the softmax function is able to be a probability distribution, aka, all your say 10 classes outputs, they add up to be 1, is because we're dividing by the value that's there. We're going to do this normalization over here, right? And if you think about it, as we try to increase, say like this is the correct class, as we try to increase the value for this class, this denominator will also increase, which means everything else will also decrease, right? So the idea is that as we try to maximize the correct class, everything else, the probability for everything else should try to decrease. And this, who here is in applied track? Can I see raise hands? Okay, so like most people. So in applied track, what y'all should have done is end this notebook, right? Like you were trying to do handwriting recognition from scratch. And what we have said just now may be a little confusing. You're like, wait, softmax should be at the end. But if you look at the code, there is no softmax. We're just putting out the layer X, right? And if you were to look at where the training loop is actually defined, the place where we pass in the actual loss function is nn.crossEntropyLoss. And you're like, wait, what is CrossEntropyLoss? That's exactly what we have been talking about for the last little bit. Is CrossEntropyLoss specifically expects logics before the softmax. And the important thing is, the reason why it expects logics before softmax is simply a numerical issue. Because when we're doing softmax, the values, these inputs, can get really, really large. So when we take gradients, things can get really, really large as well. However, we're passing this e to the power of something stuff into a bunch of logarithms, right? What is log? Well, when you have e to the power of something, you put a log around it. What happens? Cancels out, right? So the really nice thing is when you put it in, things just kind of cancel out. And this works the same way in the derivative as well. And that makes things really, really nice because when we are actually implementing, we take our softmax and we put it into cross entropy, a lot of things cancel out and things become a lot more numerically stable, right? It's less likely you're going to get, floating point overflows where, your number becomes way too big and you get not a number, which is something you may encounter in some optimization situations. So that's why we use cross entropy losses, because if you actually do the math, the gradients become a lot simpler. And by using this before we do the softmax, PyTorch handles all that math for us really nicely. And you can choose to first do the log softmax and then pass it into some kind of NNL loss, which is the exact same thing as cross entropy loss, but this time it expects you to have already passed the output into a softmax first, then a log first. So it's just you may see this in some tutorials, may see this in some tutorials. This is way more popular because it's a lot less things you have to worry about. But that's what we mean by, hey, PyTorch does a lot of this for you. And when we actually do cross entropy loss, what we have talked about is what's actually happening behind the scenes and what's making multi-class classification actually possible. Does that make sense? Okay, cool. Yeah.
Now we're going to talk about backpropagation.
Okay, so for those of you who've done advanced track, you might remember this as the training loop that you go through. So what we're going to talk about specifically is these lines right over here. Calculating the loss, which we've done already, and then per loss dot backward. So this just dot backward function really sort of covers up the unpleasant details of a very complicated process. And this process is the process of going from the end backwards through the model and updating all of the parameters that are denoted by the theta that you see in previous equations. Right. Yeah. There we go. So one thing you might be asking is, why do we go backwards, right? If we're passing in our inputs forward through the model, then why do we need to reverse the direction when we're going backwards? So we'll talk about that, but the short answer is it involves a chain loop. And when we are calculating all of these gradients with the chain rule, what we'll find is that we have to go backwards in order to calculate the earlier values of the gradient so that we can find the gradient for the entire model and update all the values of theta that we need to. Okay, perfect. So when we're actually computing the gradient, right, we've discussed before how the feed forward function is all about applying transformations one after another through matrices. So when we're going backwards, the same thing applies. So that's the thing you have to keep in mind when we're going backwards through, when we're figuring out what the gradient is for all of our functions. So the cool thing about feed-forward networks is that, as we might have mentioned last week, these can sort of model like any arbitrary function if they're of sufficient complexity. So when we take the derivative, we should be able to update them the same way. So as we can see, there is a way that this is defined. Y equals the nonlinearity function times, and you plug that into that, you would plug in Wx plus B. There we go. So when we want to update all of these weights, we have to take the derivative with respect to the weight matrix as well as the bias. And this is the process by which we do that. Right? We have a lot of different functions that are sort of composed together. And that is what generates the Y. So what we've shown here is just one hidden layer, but you can imagine there'd be a whole bunch of them. And we'd have to account for all of them when we're modeling it. So that's what the f of n minus 1, and so on. That's what the function composition indicates. So when we're taking our derivative, we're going to take the derivative of our cost, which is the thing we want to lower, with respect to each of the weights and the biases from each of the layers. And the way that we take this derivative is, this is like an attempt that we can take for our derivative, which is that we just update our weights slightly. We subtract like the performance of our model, and then we divide by that little tiny step that we took in terms of how much we changed our weights. And that's a way of calculating the gradient from the first principles of calculus, right? That's the basic equation. However, the problem with this is that it's not really all that efficient of a way. As you can see, you can always use this method even when you don't know what f is, because you just have to adjust all of your parameters and then by a tiny amount, and then just calculate the gradient that way. But if you have that many weights, then you have to adjust one weight, figure out what outcome is, and then adjust. Do that again for another weight, and so on. And if we do this, we have to go through the model a whole bunch of times. We have to do the feed-forward mechanism a whole bunch of times for just one backpropagation attempt for each of the weights and biases in our model. And as hopefully you guys saw last week, that number can get really big really quickly. So there is a more efficient way, and this efficient way is gradient descent. So when we talk about gradient descent, really what we're doing is we take the derivative with respect to just one thing, just one weight. And we do that for all of the ones just to the previous layer from the output layer. We don't like go all the way back. We just look at the derivative of the cost function with respect to these weights and this bias. And that's relatively easy to do because we know what the cost function is, right? It's going to be mean squared error or softmax or whatever you have as the as the output that you're evaluating your cost function with. And so we can take the derivative of that cost function with respect to one of the weights, one of the biases, or the previous layer. And that we can do pretty easily in terms of computation. Okay. So hopefully you guys can see that's what we're indicating here. Derivative of the cost function with respect to the weight. And that's going to be the same thing as the derivative of the cost function with respect to our activation function multiplied by the derivative of our activation function with respect to one of the variables that we care about. And we can take this all the way back as the derivative of the cost function with respect to a layer times the derivative of that layer with respect to the previous layer times that with the derivative of that layer with respect to its weights. And so that way you can access the weights of all the subsequent layers, first by calculating the derivative of our cost function with respect to the weights of its previous layer, then the bias of the previous layer, then with respect to the previous layer itself. And then you involve that in the next calculation, derivative with respect to the previous layer, multiplied by derivative of that layer with respect to its weights, its biases, and then the layer before that. So that is sort of where the backwardsness comes in, if that makes sense. That you first have to figure out the derivative of our cost function with respect to the previous layer. And then from that, you take the derivative of the previous layer with respect to all of the things that go into it. Then you take the derivative of that with respect to the layer before, and so on. Okay. So far, does that make sense? Right. So right now we've been talking about derivatives, right? And normally these are things that we have to calculate by hand. However, a computer is not going to be doing this, right? A computer prefers to work with things in terms of matrix multiplication because that's what GPUs are optimized for. So what we can do here is recognize that these weights that we're taking the derivative with respect to, they themselves are arranged in a matrix. And so we can take the derivative with respect to the entire matrix of weights rather than having to take the derivative with respect to each of the weights one at a time. And that sort of gets us better performance than having to update a single weight, then feeding forward through the model, updating the next weight, and so on, like however many thousands of times we need to. Here instead, we just have one pass, and then we have this other extended pass going backwards. So it's a little bit more complicated, but we only need to do one pass going backward to update our model. Okay. Right. So this is sort of more of the practical details about the implementation of backpropagation. And the way that it works here is that PyTorch knows what types of operations it needs to take the derivatives of, right? Because there are two types. There's either a fully connected layer or a convolutional neural network. And we'll talk about convolutional layers in a little bit, but these are sort of the standard operations. And once you know these standard operations, you can then take derivatives with respect to them. Okay. Perfect. Now, one thing you might notice is that we have somewhat of a tree structure, right? Where this is fed into by these nodes and those are fed into those nodes. So if we track the ways that the function is applied across the tree structure, what we'll end up with is a history of like what feeds in, which nodes feed into the other ones. And by tracking this history, we are able to update the weights. And then I'll pass it over to Liu to go over some more of the details about backpropagation and specifically like the implementation in PyTorch.
As we said before, PyTorch automatically calculates your gradients and it stores them in the execution tree. So this execution tree is in the background and you don't have to do anything. All you have to do is you do your operations and then at the end you call, suppose for example, your end tensor is called loss. You just say loss dot backwards and the gradients with respect to the leaf nodes of your execution trees are calculated. Yeah. And this is the backpropagation graph. As we see, we have a cost function, we have our weights, which are our leaf nodes, and through local gradient computation and the chain rule, we can multiply and add the gradients, and then get the derivative of the cost with respect to the weights. And so the beauty in this method really lies in the fact that we don't have to calculate the whole derivative at once. We can calculate the local derivatives, right? And then through backpropagation, get the final derivative answer. Yep. We just propagate backwards from the cost C until we reach the W and B. And this is actually not that hard to make. Like, if you guys were to make it in Python and so on without any PyTorch, all that you have to do is you have to work with a few basic operations like addition, multiplication, division, stuff like that. If you define the derivatives of those, you can technically represent a bunch of different, functions, and exponentiation too. Like for example, the sigmoid is a bunch of additions, subtractions, and exponentiation. If you define the derivatives for that, you don't even have to know the derivative. PyTorch will calculate it, and that's really the beauty. And you can get the gradient of the tensor, like using dot grad property. And this specific technique is called automatic differentiation. And in this case, we're doing backwards automatic differentiation. There is something, if you guys are wondering, called forward automatic differentiation. It's in the experimental phase. That deals more with like something called raw numbers and stuff like that. It's not as efficient the first run, but it's much more computationally efficient. So yeah. And so some of the math to get into it. I'm sorry, guys, you guys don't want the math. You guys do. So in this case, X is just our vector, our input vector, and W is our weight, and V is our bias. And then W is a matrix of the size N out by N in. Then this is just the problem that we formulated before. And this is how you calculate the gradients with respect to the weight matrix, right? So you take the loss, the derivative of the loss with respect to the weight matrix is equal, right, to the derivative of Y, your output with respect to the weight matrix, multiplied by the derivative of your loss, multiplied by Y. Sorry, the derivative of your loss with respect to Y. You take the product, and that's equal to this, and that's your chain rule, right? And then we can further, let's say we had multiple other layers, we can further take one, in this case, it would probably be the derivative of Y with respect to the weight matrix. And we could further like expand it and expand it and expand it and expand it and expand it until we get to where we want to get, right? Until we get into the simplest derivative to take. In this case, the derivative ends up being the derivative of the loss function with respect to Y of xt. And that makes sense, right? Because you're just differentiating this. When you differentiate this, what do you get instead? Right? So it's like rather simple, and the derivative of the loss with respect to the bias, again, loss with respect to Y, because when you differentiate this within terms of bias, you just get one, right? Even though this is a matrix calculus is very similar to just normal calculus, so it's not that different to if you guys have taken 31A, 31B. It's very similar. There are differences, but it's easy to catch on. This is just some math of one example. And, we're going to give you an example of something that's much harder to calculate, but because PyTorch does it for you, and because there are already preset functions for the derivatives, it's clockwork. It's very easy to do. And that is batch normalization. Has anyone ever had experience with batch normalization before? So normally what batch normalization does is, let's say you have a neural network. I wish I had a marker, it would have been a little bit easier to explain. So let's say you have a neural network, right? It has multiple activations between each layer. And what you want to do is you want to normalize that activation across the batch. So all you do is you take a running mean and a running variance across the batch, and then you use that running mean and running variance to make a z-score, and then you use that z-score to normalize your normalize that activation with respect to all the batch values. You don't really have to understand like the specifics of that just yet. We're just trying to show that that's a much more complicated problem, but because of the local gradient computation, because we've already preset it, we just have to calculate the derivative once. And we can just say, okay, the derivative of this is this, right? For PyTorch, just anytime you encounter this in the tree, preset the derivative as being this. So it's like relatively simple. And if you're wondering what the terms that we're learning is these two terms right here. Those are the terms that we're learning for batch normalization. Sorry, batch normalization, yes. It's the scale and shift operations. And yeah, so this example, this is like a very, very crazy example. Don't get scared because I don't know what the hell this is. I just took it from the internet hoping. I think no, Jordan took it, I think, right?
These are my notes from ECC 147. If you take the class, you won't be doing this by hand, but the professor will go through this by hand in class. The point is not for you to understand this. The point is to make you understand that PyTorch is doing all of this behind the scenes, right? Every single operation that you see on PyTorch, every single thing that looks like, oh, how in the world are they calculating gradients? It's a lot of math, but you can get there by the end because they're all built from elementary operations that we know the gradient of. And it's just a bunch of, oh, chain rule, chain rule, chain rule, chain rule, chain rule, and a bunch of matrix multiplication. And this is also why when you do backpropagation, you realize that's the part of training your neural network that's the most computationally intensive. Because if the forward process is just, oh, you multiply by a matrix, and you multiply by a scalar, the backpropagation process is a lot more complicated with a lot more math. So this is just to kind of show you is like this is what's happening behind the scenes when you're like putting all these layers in PyTorch and you're doing loss step backward. This is what it's doing just for a single layer. So yeah.
And this is pretty intense, as you can see. Thank God we don't have to know that, but yeah. So you don't have to understand this. But the beauty is, as Jordan was saying, this is all done through PyTorch for you, and you only have to do this once. You only have to calculate the derivative once, because if you know the derivative once, the general derivative formula, you can preset it and you could use any. You can actually do this yourself. If you have like a crazy function in PyTorch, and you want to implement it, you can write your own gradient, and PyTorch will use that gradient. Yeah. So back to the code. So these parts right here, all like the gradients for this are all being tracked by your by PyTorch. Let's just go through real quick. So this is your model, right? You put in your inputs to your model, and the model calls a forward function. So you have your you have your predictions, right? And your current loss, you take your predictions, you take your basket labels, which are just your true optimal values, and then you get your loss. And then what you do is you call the backwards function on your current loss. That's how the gradients are calculated for the leaf nodes. And the leaf nodes are your weights or your parameters, right? That's why when you define your parameters, always say requires gradients is equal to true. Because then they'll put into these leaf nodes, and the gradients will be calculated with respect to them. And next time, when you call optimizer step, all that the optimizer does is it has, inside it has the parameters tracked, and it steps the parameter by optimizing the parameters. So for example, if you have Atom optimizer or the SGU optimizer, it just it takes the gradient and then subtracts it with a learning rate. And there are different formulations, but that's effectively what it's doing. It just takes your previous value and it subtracts the minimum descent. So the direction of maximal descent, is that the right way to say it? Yeah. So yeah. So it effectively takes gradient descent. Gradient descent. Yeah. So that's what the backward function does, right? And yeah, that's the special thing about it. All that you have to do is that. So backpropagation summary. So you initialize your model, you initialize your optimizer, you zero out your gradients, you pass through the training data and calculate loss. And the reason why you zero out your gradients, by the way, is because during training, your gradients add up. That's how the gradients are stored. And so for each loop, if you don't zero it out, you use the gradients from before. And this is obviously nonsensical. It can lead to divergence and so on. It doesn't make sense. So you need to zero them out, right? When you pass in the training data and then you calculate the loss, you just have the loss backward function that calculates the gradients with respect to the leaf nodes, and it backpropagates through your derivatives tree. When you calculate your derivatives, and the optimizer step just updates your parameters by nodes, either subtracting the gradients with it multiplied by learning rate or so on. And yeah, you just repeat this step until the convergence for the loss is low enough. And that's it for, do you guys have any questions on this?
Do you elaborate more on zero out the gradient
Zero out, yep.
steps? Why is that necessary?
That's a really good question. So, so effectively the reason is, you see this zero graphic, you call it just before, you backpropagate through the execution tree, because you don't want to use the gradients from before.
So that's zeroing out the gradient at each of the derivatives.
Exactly. So you're zeroing out the gradients of the whole derivative tree, rather. Do you see what because there's something called a gradient buffer. So for your execution tree, there is a gradient buffer, and you don't want to use the gradients from the forward past before.
If the calculation of the gradient is happening from backwards.
Yeah.
Like,
So, okay, so specifically, this is more of an implementation detail, right? So when we are doing classification, we have one loss, right? Our one loss is just the classification loss. You're just doing backward. But the thing is, the way PyTorch is implemented is if you have multiple losses, like let's say I have a classification loss and I have like some other losses that I'm trying to like make sure my model does some other thing. What you can do is you can do loss that backward for multiple of these losses. And what it will do is remember how like the gradients are stored in the dot grad attribute of each of the tensors in the virtual model, right? Every time we do loss that backward, it adds to that dot grad attributes. So because when we're doing optimization, the gradients, if you have two losses added together, because it's addition, when you take the derivative of two things added together, you're just taking the derivative of the two things independently, right? So that's why we can calculate the gradient separately and just kind of add them together at the ends. Now the key is, every time we do backward, we do that addition. However, if we finish this iteration and we go again, and we don't zero out those gradients, we'll just keep on adding back to the gradient that we were using before in the model parameters. Right? Because again, it's just PyTorch implementation. Some, not all machine learning frameworks does this. Some machine learning frameworks does not support the whole, like when you do backward, it actually adds the gradient instead of, replacing it. If it replaces it, we don't have to do this. But PyTorch specifically adds the gradient, which is why we have to zero it out, saying, okay, we don't want to add gradients anymore. We want to start from scratch. And that is also why we first initialize any tensor that is able to have its gradients be tracked. The dot grad attribute will be initialized to a zero tensor, or a tensor of all zeros that is the same shape as the tensor itself. That represents the gradients. Because the gradient in the beginning, before you have done any backwards propagation, is 0. Right? Does that make sense?
And technically, you could put this 0 grad after. It actually doesn't matter if you put it after your step or before. The reason why we put it before is due to convolution. So you can zero it out before your whole thing. You can also zero it out after.
The only place you don't want to zero it out is in the middle, because then you have zeroed out the gradient before your optimizer could actually use it and do the sense. Does that make sense?
Yeah.
Yeah, so you can literally put this anywhere, like in this loop, besides right in between here.
since PyTorch is implement this, is there any case where we do not want to use zero gradient, but still want to use like backpropagate?
Oh, like when we don't want to do zero gradients? Again, like when you have multiple losses, right? Like let's say you have current loss equals to loss, this is cross entropy loss, we're doing prediction versus batch label. Say I want to optimize to both the cross entropy loss and also the mean squared error loss for some reason, right? Then I can do cross entropy loss equals to cross entropy these two, and I could do mean squared error loss equals to mean squared error these two. And then I have two loss tensors, right? I can do loss that backward on both of them. Do cross entropy loss that backward, and then MSE loss that backward. And the gradients for the two loss will get added together. And that's also mathematically equivalent to doing if you make a third variable that says I want to add those two losses together, and then I do backward on that loss only. It's the same thing. It's just the ease of doing so. Like you don't have to pass this like one loss like all the way out and stuff like that. And you will see why this becomes a bit more helpful later, because one of the things that you will see with more complex machine learning models is they often have a lot of auxiliary losses. So losses that come from like all different parts of the model that will be kind of annoying to try to pass them all together and to have them added together. If you just do loss that backwards in these separate locations, then it's like, oh, it just goes back to the same, goes through the same computation tree and gets added to the same grad instead of having to pass things around. So it's more of like a engineering choice rather than some sort of, rather than something that is mathematically based. And like, if you say use TensorFlow, which is like the previous popular thing before PyTorch became really popular, TensorFlow doesn't even do this whole like loss that backward thing. You use something called autograd. You can also do this in PyTorch, where instead of doing this whole like, oh, we backpropagate to get the gradient stored in part of the tensor, you can get a dictionary that is literally just the gradients themselves, and then the optimizers in TensorFlow takes in that gradient and does the gradient descent. PyTorch says, yes, you can do that. You can do that in PyTorch. You can absolutely do that in PyTorch, but it's a little bit more complicated, and PyTorch just decided to go with this approach instead, where the gradients are kind of hidden away from you. You don't get to touch the gradients. PyTorch gets to, do whatever it needs to do with it. So again, it depends on the machine learning model, how the stuff is implemented. Does that make sense? Yeah.
And next, we will go to CNNs. Oh, yeah, we want to. Does anyone else have any questions on this? You guys are good. All right.
Perfect. Sparsh. Oh, this after. I'll charge.
Well, okay, we will see whether we run out of battery or whether we get through this presentation. One of two things will happen. Okay, so last week we talked about fully connected layers and we hinted at using convolutional layers this week. But first, to motivate this question a little bit, let's investigate like why we need convolutional layers in the first place. Because for those of you who did advanced track with MNIST, you might notice that when we took our images, we had 28 by 28 pixels, and we just flattened them into a 784 by 1 vector. And then we just worked with that vector, and we plugged it into a fully connected layer. I've abbreviated that as ACM for simplicity. And that worked fine. We got like 99% accuracy. So the problem with this is that we had 28 by 28 pixels, which is like terrible. Like if your images had 28 pixels in them, your face wouldn't really be all that visible. So even just something that's 100 by 100 pixels by 100 pixels for RGB, so 3 channels instead of just the 1 channel for MNIST, that amounts to 30,000 elements inside your input tensor. And so if you flatten that out and you connect it to, say, another layer that has 2 neurons, you'll end up with needing to learn 60,000 weights and 2 biases. So that's going to be 60,002 parameters that your model has that just explode into being because of the size of your image. That's a lot of parameters for something that's not really that complicated, right? If our single first layer just connects to 2 neurons, that is already a huge number of weights. And the more weights we have, the more time it will take for a model to learn because our parameters would occupy a higher dimensional space. And if you are in a higher dimensional space, that means you require more investigating before you can sort of find the minima in your space. So ideally, we'd like to minimize the number of parameters if possible. And that's really what convolutions are for. It's so that we don't have to just go straight to 60,000 weights. Instead, we can reduce this number so that when we finally do go to our fully connected layer, what we'll end up with is something that's a bit more manageable and less parameters overall. So the way that a CNN works is that rather than plugging in our image directly, instead we're going to run a bunch of filters on it to create things called feature maps. Then we'll run filters over those feature maps to generate higher order feature maps, and so on and so forth. So if you run a feature map over an image the first time, for example, you might pick out a lot of like vertical lines or horizontal lines, or if you run it again, maybe you'll start picking out some curves, more complicated curves. And if you keep doing that, eventually, if you're like trying to classify animals, you might have some feature map that appears to really correspond really nicely to like things that kind of look like dog heads from like that are translated across various areas. So that's essentially the idea. As you keep applying these filters, you end up with feature maps that are more reflective of the properties of your image. And once you get to the point where you're satisfied with your feature maps, then you sort of unpack that into a single dimensional vector, plug it into a fully connected layer, and off you go. So the reason that this works is because you only have to learn these filters as opposed to learning those weights. And these filters will be things like 3 by 3, 5 by 5. You might have like bigger like kernel sizes, but it's still not like the same size as the image. So as the image keeps shrinking, as you keep applying these filters, you just need to learn these filters, and then you learn the weights for the fully connected layer. And that will end up being a simpler way to model more complexity, which means that we can train our models more efficiently. So it takes fewer passes and fewer epochs to get to 99% accuracy. Okay. So this idea of applying a filter relies on something called convolution. So we'll talk about convolution in a little bit, but a really quick way of thinking about it is that if you have an image that's just like a huge square, then you're going to take your filter and you're going to run it over the image like this. And then you're going to generate some numbers that we're going to then put into an array. And we'll sort of make that more concrete in a little bit. So does anyone have any questions about what was covered so far?
Specify what do you mean by convolutional?
Oh, yes, we're gonna go into convolution in just a little bit. Anything else? Okay. Right. So when we're talking about a convolutional neural network, it relies on this concept of these feature maps. So you'll start off in this area where you have your input image, then you apply a series of convolutions with kernels, and then once you're done getting your feature maps to where you want them to be, you'll end up with a single flattened layer, plug that into a fully connected layer, which is trained as we discussed last week and this week. And then you finally add your outputs, which are the predictions. So we've talked about this whole thing already, right? We talked about the feedforward last week. We talked about backpropagation this week. We've talked about how softmax generates probabilities. So really the part of this that is sort of mysterious at the moment is this area right here. And that is the convolution part of the convolutional neural network. Okay, so as was asked just now, we're going to go over what a convolution is. So how many of you have taken EC 102? So this, you sort of like go into a lot of detail on convolutions in EC 102, but the main idea with a convolution in the continuous case, as the graph shows, is that you have some reference function, which is represented by this blue curve here, and you have another function. And you're taking that other function and you're dragging it over the blue function. And as you drag it, what you want to keep track of is the area of that is encompassed by sort of, hold on, I'll wait for it to get there. Yeah, this area, right? The area of the intersection.
The yellow part?
Yeah, the yellow part. And the reason it's the yellow part is because I will wait for the animation to go back. Is because it's 0 everywhere else, right? Except in this area. So you're going to be multiplying this value by the values of the function here, and you're going to be doing an integral. So that gets you sort of the product of the areas of the two graphs. And you do that as you drag it. Normally you'll drag it from negative infinity to plus infinity. In practice, you don't need to go to infinity. And also in practice, we'll be working with discrete cases rather than continuous ones. But this is sort of the abstract sense of what a convolution is. You have some reference thing, and then you're taking another reference, and you're taking another thing and dragging it over the reference thing and taking a product of some kind. Okay. So as we said, that was convolution in the continuous case. If you want to work with pixels, however, of course, those are not continuous, right? It's individual pixels, right? You're going to have like some discrete number of them. So the idea works the same way, but it's a little bit simpler. The idea here is you have a kernel and you take the dot product of the kernel with the part of the image that it overlaps with, which you can see here. And that dot product goes in the square there. You shift it over and then take the dot product again, that goes in there, keep shifting it over like this, and then you keep track of your dot products. And then once you've gone to the end, then you shift it down here, run it over in the same way, calculate the dot products in the same way. So again, I'll just like let this run so you can see it again. But you can see that it's taking the dot product of like all the parts that are overlapping. And typically, in order to make sure that this dot product thing works out, we'll like pad our images. There's like an implicit padding of zeros all around here, so that if the filter like sort of goes off the image, it's just gonna get multiplied by 0. So there's sort of an implicit padding of zeros around here, even though it's not shown. But that is the process of convolution here. You just dragging the kernel and then keeping track of your dot products and arranging them in the array. Okay, so hopefully you can sort of see the analogy between this and the continuous case, in that in both cases you have your reference thing. In the continuous case, it was the blue curve. In this case, it's the image, and then you have the other thing that you're dragging across it. In the continuous case, that was the red rectangle. In this case, it is the kernel. And then you keep dragging it, take a product. In that case, it was an integral over the products values of the functions. In this case, it will be the dot product between the values of the kernel and the parts of the image that it is overlapping with. And you just keep track of that as you drag it along. And that ends up being the values that you put into the output array that is the result of the convolution. Okay. So far, any questions on the process of convolution? I'll go back to the visualization. Because this is sort of like really key to the whole idea of like what convolution is. This sort of image is the one you should have in your head.
I guess just a tricky question. So the border, I see that it takes value. I'm not sure if it's like taking the value on the other side to fill in the empty space, or is it like expanding the data to offset?
Oh, yeah. So that's what I meant by implicit padding with zeros is you can imagine that this is
This
0,
one is
0,
on the-
0, 0, and there's just zeros all around.
But this set is 776.
Oh, yeah. That is because if you look at these values here, it's just showing the intersections. Because there are like 9 values and it was showing 6 over there. That's right. But the idea is still the same. There's like an implicit padding there. Okay. Okay, perfect. So that's the convolution. So when you talk about a convolutional layer, what you talk about is having the filter run over your image, but the kernel itself, right? If you go back to the animation, these values inside the kernel, these numbers right here, these are the things that our model has to learn. These are the weights, quote unquote, that have to be learned. So when we talk about like what this filter is, this filter is going to have 3 dimensions, right? It's going to have the height of the filter and the width of the filter. Typically, those are the same because square filters are just nice. And then the number of channels. So this is going to be like, if you have an RGB image, then you're going to have 3 channels. Okay. The other thing you need to talk about when you talk about how the kernel gets applied to your image is the stride. So as we saw before, right, the kernel itself was moving 1 pixel at a time. We don't have to move 1 pixel at a time. We could move 2 pixels at a time if we wanted to. So if your filter is like this, then at the next time it moves 2 pixels instead of 1 pixel. And then that would be a different stride. And the same thing would apply, of course, not just going side to side, but also up and down. Instead of just going down to the next row of pixels, you can always go 2 rows down or 3 rows down or whatever. And that's determined by your stride. Okay. Nice. Okay, so we talked about this. Okay. So this is sort of a summarization of all the parts of how the filter gets applied to our image. So I have a question for you guys. I mentioned that the things that we have to learn are the values of our filter, right? Like those numbers inside the array for the kernel. So how do you think our model would learn these values? As a hint, we have talked about it earlier today, but in a different context. The answer is that it will learn these values through backpropagation. So as we mentioned before, right, you can backpropagate through like a whole bunch of things. You can backpropagate through batch normalization and like lots of other functions that are like kind of unpleasant to go through. And this is another thing you can backpropagate through a convolution. If you want more details on how precisely you backpropagate through a convolution, I have an article on my laptop, but it is, well, it's not really all that math heavy, although it can be sometimes, but the article is not that math heavy, but it's a lot of details of like keeping track of the indices as you like take dot products and stuff. So just suffice it to say, a backpropagation algorithm exists that will take you through backwards through the convolution so that you can figure out how to update the values of your filters. So you can improve your browser performance on the next feed forward pass. Okay. Perfect. So once you've applied a filter, you will end up with a new array. So typically the paradigm is that once you've applied a convolutional layer, you will then apply a pooling layer. And what a pooling layer does is it will take like a cluster of pixels and it will reduce them to a single value somehow. So you can maybe take the maximum of this cluster of pixels, you could take the average of this cluster of pixels, you could take the minimum of this cluster of pixels, the geometric mean, whatever. There's like a lot of things you can do. Typically, we'll go with the maximum because that encodes the most information about that cluster of pixels. But we can experiment with other things if you would really like to. Right. So this is a visualization of why we would like pooling to happen. So you can see that our image, or like I'll say feature map, our feature map has shrunk dramatically from here to here by applying the pooling layer. And that's helpful because, as I said, we don't want to have too many parameters we want to learn, because the more parameters we have, the more expensive it is to train the model. So you hopefully can see how the sort of chunking has been done. And of course, if you had bigger images, it would still, this would still be a 2x2 pool size, which means you'd be taking squares of 4 pixels at a time. And if you had a 3x3 pool size, you would have like squares of 3 pixels at a time, and so on and so forth. Right. Okay. Right. So let me go back to this. Okay. Right. So hopefully now this is a little bit less mysterious what's going on here. Right. You start with your input image. You apply a convolutional layer. After that, you apply a pooling layer, and then of course activation function, and then likewise do the same thing, convolution, then a pooling layer, and then activation function. Yes.
Yeah, I see that in your previous slide, the pooling is reducing the size of the
Yes.
picture. But here, why does it also get taken?
Oh, that is because we talked about learning a single filter, right? That we're running over the image. But you can learn multiple filters, right, for any layer. And then those filters will have their own results, and you can concatenate them together.
Do
So
you mean those filters do not cover the same range, or they have different filtering principle?
they would have to be the same size, or have the results would have to be the same size, so you can concatenate them
So
together.
the cluster is the same for the filters.
Yes, yes, the cluster is the same. But you can have like a bunch of different filters looking for different things, and the results of them will be then concatenated in like a third dimension. And then you can like apply that same thing here. So that way you can like look for more features in a single layer.
Can I just clarify real quickly? Yeah. So just to like, that may still sound like a little confusing because it's like, okay, what do you mean by having like a cluster of them? Can I write with this? Oh, can this be erased? Yes, I can. Okay, cool. So if you like, we talked about like the number of parameters in like a convolutional layer, right? Like let's say, we have a filter that's 3x3, right? Let me see them. 3x3. Is this like sort of visible?
That doesn't work.
Cool. So all right. You know what I'm gonna do? Okay. So let's say we have a layer that's 3x3, right? Or a filter that's 3x3. And if say our input image also has 3 channels, right? RGMB. It's a little confusing. So let's say we have a 5x5. So our input channel is 5x5. Then because we have 3 channels, because we have 3 channels in the input image, for each of these 3 channels, we will want a filter for every single one of them. So then we have 3 times 5x5. So the 5x5 part is the actual like filter itself. And let's say we want to then output it to a filter number of say 32. And the reason for doing this, so then our filter size would be 32 by 3 by 5 by 5. And the reason we want to do this is because for each of these filters that we're applying on the 3x3 image, on a 3-layer deep channel, what's actually happening is for each of these channels, we have a filter that outputs to each of the 32 channels in the output, right? And then for the second channel, we also have a filter that outputs to all the 32 channels in the output. It's kind of like a fully connected neural network, but just in the channel dimension. And the reason why that's a lot better than just using a fully connected network is because we're doing this in the channel dimension, and the channels never get too big, right? They're like 32, 128, 256, something like that. But if we were to just do a normal fully connected network, what happens is our image size can get really big. What if you're dealing with an image that's 256 in resolution? You have 256 times 256, that's huge, right? But with convolutions, that gets to be a lot smaller. So if you were to try to visualize this, I'm going to try to draw again. Like, what's happening is, like, if you imagine one layer like this and another layer like this, we have a filter that leads from that one layer to a pixel on the second layer, and that's one filter, right? And then we have a second one for the second output layer over here. So we have a second filter that's different that we train separately that maps to the second layer, right? And we keep doing this for all of them. And you may be wondering, okay, those three filters, what do we do with their results? We just add the results together, just like we do with fully connected neural networks. Does that kind of make sense? So yeah, by doing so, like if you imagine, like, okay, the second layer has 32 channels, then we can inflate the third layer to say 64 channels, 128 channels. And as the filter size, we usually also decrease the filter size as layers get deeper. As the number of channels increase, the size of our feature map will also get smaller and smaller and smaller and smaller, because there are techniques that we will talk about. I don't know if we talk about this week, maybe we'll talk about next week, called pooling and strides, that tries to downsize the feature maps. And what happens is when we're doing so, we're actually doing less filters per time, right? Like we're going through, like the feature maps getting smaller and smaller and smaller and smaller. So every time we're doing this like filter dragging thing, we're actually going through less area. So by doing so, we're almost like extracting more and more and more features on the image. So yeah, like you can kind of see that happening here with like, having a bunch of filters. And the reason why we want to do this, having a bunch of things like convolution features with downsizing connect to each other, is if you think about it, if we start with our original convolution operation, right? Each of these 3x3 kernels can only see a 3x3 portion of the image, which is fine, right? Like with most images, we want, the important thing is like the local patterns. Like, hey, is this a person, right? Like, do they have this pattern that looks like an eye as you drag it through? However, the global information is still very important. The relation of, say, I have hair up here and then my chin's here, my two ears are on two sides of the image, right? Like, that's also important. And the way we're able to capture that information is as we do a bunch of different convolution layers, the deeper layers are able to see almost more of the original image because we're doing this constant downsizing, right? If the first convolution feature is able to see 3x3 portion of the original image, and we were to downsize that feature map by a factor of 2, then the second convolution layer will be able to see the 6x6 portion of the original image, then a 12x12, then 24x24, and you can see how that grows really quickly, right? So intuitively, what we are trying to do with a convolutional layer is we're trying to model this like fully connected layers ability to see the whole image at once, but we're doing so by having a bunch of really deep layers. The deeper the layers, the more global it is looking at, like the more global features it is looking at. So like if the first few layers are saying, is there a curve here? Is there a curve over here? Is there a curve over here? The last feature is saying, are these curves in these corresponding places? Like on a very high intuitive level. Does that kind of make sense with convolutional neural networks? Yeah.
Oh, whoops.
Like, it doesn't very comfort, like, if not, if it's just using neural network, that's kind of like using the convolution with just with the other size of one and pooling.
Kind of. Sort of. Not really. That is actually a technique we'll talk about next time. That actually helps you to really reduce the number of filters. Because if you think about it, what we're actually doing with like using like fully connected layers is we're not having different channels. We're not having different, like depth of the image, right? We're just treating this image as the depth. So really what's actually happening is we're like a fully connected layer is the same as saying we take this image, we thin it out into one really long image. We treat instead of the different pixels of the image as the channels, and we have a 1x1 image, and we have a 1x1 filter. That's what, if that's what you're thinking about, that's how it's equivalent. But like the important thing to remember is because we are first doing this filter thing, it is able to understand spatial relationship, even if you shift the image around, right? If it's shifted to the right by 5 pixels, it will look relatively the same. The convolution layers are still able to capture the same features. And second, the way we're able to capture more and more and more features from the input image is by kind of inflating this channel size. And by doing so, we're starting to capture more and more global features. So if like this portion captures just like a tiny bit of the leg here, then when we're at this layer, it's able to capture the whole image and say, okay, we have this shape. Does that make sense?
Yeah. So again, just to recap, the primary reason that we have like multiple channels here is that we have multiple filters that are running through over this. And each of them is going to generate their own feature maps. When we concatenate them together, then we can learn from these feature maps by taking out another filter and like going through these feature maps. And that will combine the insights from each of the individual ones. And we'll go through like something like what those features might look like in a minute. But the reason that just a regular fully connected layer is different from that is that it's sort of like you take your image and you just like apply a giant filter over it, and then you get the value of 1 neuron. Apply another giant filter, get something like this. But because you're just applying one giant filter instead of looking for like actual features by running your filter over your image, what you'll end up with is something that is sort of suboptimal at finding like specific parts of the image that might be relevant to whatever sort of image classification task you're doing. And we'll make this more concrete with a visualization that's coming up shortly. But that is sort of like the insight that you get from feature maps that you don't get from just the regular layers of a fully connected network. Okay. Perfect. So before we get to that visualization, I just want to go a little bit more into the implementation of this again to make it sort of more concrete, which is that if you are running this kernel over this image, then that's going to lead to some output of some different shape, which you can see here. This is your image, this is your feature map. And what you can see here is that the output is smaller. And the reason for that is that the dimensions of the output are determined by these formulas. And that's where W is the width of the original image, H is the height of the original image, D is the number of channels in the original image. The padding is like, if you want to add like zeros on the edge, how much should you add? Should you add 1 row, 2 rows? Should you add 1 column, 2 columns of padding, and so on? And we're assuming that you like add padding uniformly around the whole thing. That's why it's 2p from this side to this side. And the shape of that, as you can see, is going to be W, which is the initial image, minus K, which is the kernel size, because this kernel is only going to go through this image 3 times before it gets to the end, right? We can see that. And then likewise for the height, you're going to go down like once, twice, 3 times. So because of the size of the kernel, you can't go down through the image in its entirety. So instead of having a 5 by 5 in the output, you're going to have a 3 by 3. So the bigger your kernel, the greater the change in the size of your output. And in the extreme case, if the kernel is the size of the image, then the output will be one single pixel, and that is effectively a fully connected layer.
I felt like there should be a mass equation between P and K.
And relation between
Like
P and
2P equals K plus 1, K minus 1, or K plus 1.
Oh yeah, you can. Well, I mean, you can establish that relation. Yes, I mean, the amount of padding that you want really depends on the output.
The size of the.
Yeah. So you can like rearrange that equation to solve for different things, depending on whether you know what size padding you want, or what size stride you have, or what size of the output vector you want.
Also, another thing is, if whenever you're confused, is like how much padding should I add, and yada yada. If you go to PyTorch right now and you go look at the documentation for their conv2D layer, which is like their 2D convolution layer, which is what we use for computer vision, you realize they have really great formulas, really great documentation. Like you just click on that, you realize they have like really incredible documentation for like exactly, well, like that's how it works, and then they will tell you if you scroll down, like what the output size will be. If you keep scrolling, over here, somewhere there, right? Like you see, like they tell you what output size it's going to be. It's somewhere here, but like, you know, they tell you, and it's really nice because whenever you forget, You just go, okay, I want my output, say I started with a 30 by 32 image. I want it to be a 16 by 16 image and have a 3 by 3 kernel. What do I need to set my padding so it's that? It's usually 1. But like, you can start to figure that out. And then like, like if you put the wrong value, it's no big deal, because what will happen is you try to pass an image through your model, and your model just screams at you being like, oh, the dimensions doesn't match. And then you will like, okay, I may have to change my path.
And one thing you might notice is that this kernel here, right, it's got zeros in the bottom layer here, and it's got like ones here. So you can think of this as it's sort of scanning the image and like looking for like triangles of that look something like this. I don't know if you guys can see this invisible triangle here, but yeah. So that you can think of it as like it's scanning through the image and looking for like instances of that, right? And you can imagine if you wanted to instead look for vertical lines, then your feature map might be something like 0, 0, 0, 1, 1, 1, 0, 0, 0. And if you like run this over, right, it's gonna like have a higher value when these are highly positive, and if you say want to make these negative, then that's gonna like really spike when you have a vertical line in that area. And so, of course, different feature maps have different interpretations. Some don't necessarily have immediately like human interpretable interpretations. Yes.
Question. It's not entirely math like related, but like let's say we take a problem of like object detection, or like basically like saying if there's a cat in a image or not, right?
Yeah.
So it's gonna basically get its features, which are like the outline of like how a cat's face will look maybe, or something like that, right? So that's applied over here, right? When it's basically scanning the entire image with the lines and the curves.
Yes, kind of. So it's not like any given feature map is immediately going to start scanning for like this image of a cat's face.
Yeah.
But like an initial feature map from earlier on in the layer might spike if it like sees like really sharp horizontal lines that might correspond to whiskers, might correspond to other things.
Right.
And then subsequent feature maps will take insights from those feature maps. And then like maybe later on in the convolutional layer, like vague cat-like shapes might be things that like would really make any individual feature map spike.
Got it. I have another question. So, like, if we keep like decreasing the size of our image by like using this technique, won't we lose like details about the image? Because essentially here you're just condensing the image into smaller pieces, right? So
the idea is that we want to discard information that's not useful and extract information that is. So like not every single pixel that's in an image is going to be useful.
Right.
But in this way, when we like run the convolution over it, every single pixel in this feature map is more meaningful than the one in the previous one.
got it.
Okay. And then this is an example of like sort of early on in the process, what different feature maps might look for and why CNNs are better than fully connected layers. Because if you look at like what would make a fully connected layer spike in the beginning, right? You see sort of, this is supposed to be looking for an 8 here, by the way. But like the things that make these intermediate layers spike are not really all that defined. They're kind of nebulous. But here, if you look, these feature maps, which these filters generate these feature maps here for your input image, you can see these are like starting to look for features that are relevant, right? Like they're responsive to loops, they're responsive to vertical lines and so on. And when you run these feature maps over the image of a 9, you can sort of see like what features really sort of pop out in the feature map in a way that is less obvious here with the fully connected layer that's trying to look for what this 8 is. Okay. Perfect. And then, no, let me move this down. Okay, yeah. So one thing that I've stated just sort of offhand is that some sort of input would make these feature maps spike. Like they're gonna get super excited, like this is the thing that they're looking for. And I just wanted to like quantify that a little bit, because up until quite recently, actually, the layers of like neural networks and so on were fairly hard to put in a human interpretable context. But there's a technique that exists that you can sort of use to like probe models and like try to figure out what they're looking for. It's not perfect because like explainable AI is still like a huge field and like very much in its infancy. But one thing that you could use to try to determine what would make some given feature map spike is backpropagation, right? Gradient descent, where you treat the pixels of your image as the input, and then you treat the values of the feature map as an output, and you try to like maximize the feature map of your output so that it looks like a completely white screen, because that means that your feature maps here is like going crazy, like this is really activating the feature map. And then you do gradient descent to try to figure out what the initial values of your image need to be for all of its pixels, so that you can really get an excited value for the feature map. And if you go through this enough times, you'll end up with like some sort of like psychedelic, like distorted image that will correspond to what the feature map is looking for. And so that's basically, in a sense, like how you can sort of try to interpret what these feature maps are looking for, by trying to see what would excite them most, and then try to like detect patterns in that image. Okay, so that is the end of our presentation today. Hopefully you guys understand maximum likelihood estimation, gradient descent, and CNNs better than you did before you guys came in. And we'll stick around for a bit if you guys have any other questions, but
This is next slide.
yeah, no, there's my next slide.
Just go to the ending slide.
Yeah, this is
Oh,
the
it's
ending
the
slide.
Okay.
Yeah, there.
Oh, wait.
There we go. Okay, yeah. So yeah, this is the attendance code today. Next week we're going to talk about modern CNN architectures and RNNs. So modern CNN architectures, you're actually going to see how CNN networks are being used today. Like how are all these really large networks able to classify images really well, and how are they used today? And then along with RNNs, which are recurrent neural networks, and things that are able to process sequential data, which is something that you may be using in applied track if you go the RNN notebook route. So yeah, hope to see you next week.